Hello everyone, my name is Anastasios Andronidis from Imperial College London, together with my collaborator Christian Kadar, and I'm here to talk about SnapFuzz, a high-throughput fuzzer for networking applications. Before we dive deeper into what SnapFuzz is and how it works, I would like to talk about fuzzing and what exactly fuzzing is. Fuzzing is a popular technique in which a target application like an FTP server or a LibreOffice is hammered with a lot of auto-generated inputs. The goal here is to make the application crash and in this way discover new bugs and vulnerabilities. It is not uncommon for fuzzing campaigns to last as long as days or even weeks, but one of the most important factors for a successful fuzzing campaign is the number of generated inputs per second. The more, of course, the better. So why fuzzing is so important and why would someone spend weeks of CPU time for fuzzing? With fuzzing, Google has discovered more than 25,000 bugs in their products and over than 22,000 in open source projects. Fuzzing is also the golden standard across the industry for finding security vulnerabilities, also known as CVEs. While fuzzing is so effective and popular, it still has some important pain points. Most importantly, fuzzing requires significant engineering effort, which in some cases, like network servers, is quite high. We specifically mention and focus on network servers because network servers often implement a communication protocol which might be stateful. Statefulness is particularly hard for fuzzers as they require the fuzzer to be aware not only about what commands they have to send to the target server, but also they need to be aware of the order and interdependency of these commands. In addition, network servers might also have side effects, like writing files or sending information over the network, which might require the fuzzer operator to implement isolation or an environmental reset for every fuzzing iteration. So what is the current state of the art for dealing with stateful protocols, isolation, and environmental or state reset? Today, we mainly have two ways for dealing with this problem. Firstly, we can use tools like libfuzzer, which they can access the source code and invoke parts of the target application like unit tests are. Of course, this method requires significant engineering effort and internal knowledge, and it also has the limitation that the system is not tested end-to-end. A second way is to use tools like AFLnet, which exercises the target application end-to-end. Of course, this solution comes with its own set of problems and a huge performance penalty. The main issues this method faces are firstly, how do we reset the environment? And secondly, how do we configure our network parameters with respect to send and receive delays? To make things more clear, let's see an example from our artifact. The DICOM image archive server is a multi-threaded file database which has a stateful communication protocol. In order for this application to be fuzzed properly, for example, with AFLnet, on every fuzzing iteration, we need to delete any files the server writes, so there will be no interference. And secondly, we need to configure three different network delays from the fuzzer's perspective. The first delay is about waiting for the fuzzer to initialize and being able to accept inputs. Second is about adding some delays between consecutive inputs so we don't overwhelm the server and packets are dropped. And thirdly, the fuzzer doesn't know if the target server is waiting for more input from the fuzzer, is waiting to fulfill a request, or is sending some response. So the fuzzer needs to add an additional delay before switching between sending and receiving. In addition to all this, the server application has a long initialization phase in which configuration files and external libraries are read, which decrease performance of the whole system significantly. So is there anything better we can do to make fuzzers like AFLnet to go faster? Introduces SnapFuzz, a fuzzer that builds on top of AFLnet and which completely automatically resets environmental state, isolates the target application from side effects, eliminates all communication delays, and snapshots the target for faster iterations. SnapFuzz achieves significantly higher performance than competitors like AFLnet, from 8.4 times to 62.8 times faster in 5 popular server applications. But how does SnapFuzz achieve these results? SnapFuzz consists of 6 components that all contribute separately to our performance gains. We will first discuss one of our major components, the SnapFuzz protocol. So we saw in our example before, fuzzers perform several checks and add several delays to ensure communications are in sync between the target and the fuzzer. This is because the fuzzer doesn't know when to send or receive packets from the target. The SnapFuzz protocol addresses exactly this issue by making the fuzzer aware of when the target is ready to communicate and if the target is ready to receive or to send information. SnapFuzz is able to know exactly the state of the target because SnapFuzz is intercepting all the target system calls in a similar way that strace in Linux does. Of course, strace and ptrace are very slow. This is why SnapFuzz is using Saber, a userland-only modular selective binary writer, to efficiently intercept the target application. You can find more about Saber in the following link. For us, Saber is a library that we use to transform the system calls of the target application in more efficient alternatives. For example, SnapFuzz transformed TCP/IP communications to the faster Unix domain sockets. Or SnapFuzz can completely eliminate sleep system calls to avoid unnecessary delays. Now let's go back to the SnapFuzz protocol and how SnapFuzz makes the fuzzer aware of the communication state of the target. In this example, we see the current architecture of most networking fuzzers, like AFL-net, that are receiving and sending information to the target. As we discussed, this architecture is quite slow. SnapFuzz is different. We wrap the target, and as we discussed, firstly, we replace the TCP/IP with the Unix domain sockets to increase performance. And then we add an extra system call right before each receive and send attempt of the target, in order to inform the fuzzer about the intention of the target. By introducing our own protocol, SnapFuzz achieves significant performance gains as it completely eliminates all manually introduced delays by automating the state awareness of the fuzzer. The second most important component of SnapFuzz is the smart deferred fork server. The fork server is a common pattern amongst fuzzers and it snapshots the application in order to avoid restart overhead. To make things concrete, a program often loads libraries just before it enters its main function. Common fuzzers like AFL and AFL-net add the SIM just before entering the application's main in order to pause the execution right before main starts. When the SIM is executed, it uses a fork system call to create a clone of the memory state of the application. When the SIM is executed, it uses a fork system call to create a clone of the memory state of the application. This clone is actually a snapshot that then can be allowed to continue executing. By utilizing this continuous forking, AFL and AFL-net completely avoid reloading the application libraries and thus increasing performance. Unfortunately, though, any application code that loads files or makes expensive cryptographic initializations still remains inside the main function. The fork server architecture of AFL can snapshot expensive initialization phases, but the fuzzer operator has to manually alter the source code of the target. SnapFuzz, on the other hand, because it has access to all the target system calls, is able to snapshot the application at a much deeper state. We do this completely automatically and without any code modifications. The only limitation of our method is that we can snapshot the target only before any network communication or thread generation happens. Thirdly, SnapFuzz offers an in-memory file system. By intercepting all file system-related system calls, SnapFuzz is able to understand which files are important to the target and loads them in the memory space of the target. Thus, when the target attempts to read or write any kind of files, performance is higher as everything now is in memory. The in-memory file system also works in tandem with the smart fork server in order to automatically reset any writes of the target to these in-memory files. SnapFuzz offers more components that follow the same strategy of replacing system calls with more performant alternatives. For example, we offer a smart affinity mechanism. We also eliminate developer-added sleeps, and we also avoid any kind of STD out, STD error writes. You can read more about them in our paper. Now, let's discuss our results. As we can see, SnapFuzz has significant performance benefits ranging from 8.4 times to 62.8 times in 5 popular server applications against our baseline, which is AFL-net. In addition, we have seen that all SnapFuzz components contribute to performance benefits. For example, in our DNS benchmark, the two dominant components were the SnapFuzz protocol and the Smart Defer Fork server. While for the FTP server, it was the SnapFuzz protocol together with the in-memory file system. And for the live streaming server, it was the SnapFuzz protocol with the Smart Affinity component. For more details, of course, you can check our paper. Lastly, due to its sheer performance, SnapFuzz was able to find more bugs without us changing any algorithmic parts of AFLNet. Thank you for listening. You can find more about SnapFuzz and our artifact in the link here. More than happy to take your questions. Thank you.